So today we're going to review material on electrochemistry using version 2 of the document. Is that the only one I handed out? Okay, good. Because there is a version 1, obviously. All right, so let's take a look one by one, highlighted ones. For the reaction of sodium bromide with chlorine gas. Sodium bromide with chlorine gas. And that was diatomic. To form sodium chloride and bromine. Oh, that's not a gas. All right. It's a liquid, isn't it? Fluorine, chlorine are gases, bromine's a liquid, iodine's a solid. The phases don't matter in this case, except for the gases, because we need to know it's a gas in order to assign diatomic to it. Well, that one we do. Okay, the appropriate half reactions. Okay, we did introduce half reactions. Okay. So in order to determine which is the oxidation and which one's the reduction, we need oxidation states, correct? Okay. So alkaline metals are always +1. So that means bromine has to be a -1. Elements are 0. 0. So here we have another +1, and here we have another -1. Okay. So which one's well, what happens from sodium to sodium? Nothing happens. Right, it's a spectator. We could just as easily write this one as Br- and Cl- for oxidation and reduction purposes. But what happens to bromine is what? It goes from a -1 to a 0. Is that oxidation or reduction? Oil rig, oxidation is loss. It had to lose 1 electron to get to 0, didn't it? Okay, so this is the oxidation step. That means this one has to be the reduction step. Okay, so they got them in oxidation, reduction, oxidation first. So let's do them in that order. So this is going to be the bromine ion. And it's going to be Br2. Okay, so if it's oxidized, it has to lose. That means the electrons have to be on this side. And that's 1 electron per bromine, but we've got 2 of them. So we need 2 here, and we need 2 there. Okay. All right. Reduction step. That's chlorine goes to, yeah, they don't put the phases in there, that's okay. Goes to Cl-. Since it's a reduction, electrons are on this side. And a similar situation, we have 2 chlorines here, 1 electron per chlorine. So there we go. Okay, so which one fits? Let's see, 2 bromine, looks like B. Yeah, B fits. Did that one give anybody trouble? No, I wouldn't think so. We're starting off simple. Do we put one on the board and have somebody come up and work? You're unanimous. No. All right. All right, number 2. Ammonium metavanadate. So we're only interested in the vanadate part. Ammonium is a spectator in this case. reacts with sulfur dioxide in acidic solution as follows. So we've got CO3 minus and SO2. And they put a coefficient here, X and Y. And another X here for VO2 2 plus, and Y SO4 2 minus. Okay, we want to know the ratio of X to Y, right? Since they've got X here and Y there and X here and Y there, they're telling us that they should be the same values, right? So that's what we should expect based on the problem. But we need to balance it in acidic solution. Okay, so we got to do oxidation states. Where do we start? Well, oxygen's always -2, almost always, except for peroxides, right? So if oxygen's -2 and we have a -6 total oxidation state here, we got to hold one of those out for the charge. Right? So that means this vanadium is +5. How about this one? Well, it's -2 times 2 is -4. It's neutral, so we got to neutralize all of them here. Okay. Again, there's only one oxygen here, -2, right? But it's got to be a plus. So we need 2 more pluses than minuses. That means we actually have to neutralize a -4. Right. You can check yourself. +4 and a -2 is a 2 plus, right? Okay. -2 times 4 is -8. Hold 2 of them out. That means this sulfur is a +6. Okay. Now that we have our oxidation states, we can determine which is reduction and which one's oxidation. Right? Which one's oxidation? Oxidation is loss. So we have to go more positive. Let's see, +5 to +4. No, that's not it. +4 to +6. Yeah. We had to lose 2 to get from there. So the oxidation step has sulfur dioxide yielding sulfate ion. Okay. That means the vanadium has to be the reduction step. Okay. So what's the next step? Balance all elements except oxygen and hydrogen. So we check. 1 sulfur, 1 sulfur, 1 vanadium, 1 vanadium. Good there. Now we balance the oxygens. How do you balance oxygens? With water molecules. Right. So we have 2 oxygens here and 4 there. Which side does the oxygen need to go on? This side. So we need 2 oxygens here, right? That's 2 oxygens. But we added 4 hydrogens. So the hydrogens have to balance over here. Okay. All right. We got 3 over here and 2 there. That means we need another oxygen over here and 2 hydrogens over here. Okay. Now we'll do electrons. So we had a sulfur here that was at +4 and it went to a +6 oxidation. That means 2 electrons had to end up over here. Because 2 minuses and a +6 is a +4. Okay. All right. So this side reduction, that means we need electrons on this side. Well, how many? Well, only 1, right? Yeah, just 1. So now we can put them together, right? Wrong. Got to balance the electrons. Right? You got 2 electrons up here, you need 2 down here. So we're going to say 2 times that one, 2 times that one, 2 times that one, 2, and 2. Now we can add it here. Or do we need to go that far? Or do we already have our X's and Y's? Right. X is in front of here, and the Y is in front of there. So it's 2 to 1, isn't it? Yeah. We don't have to go all the way. We found our answer. Now, if we did, of course, we'd have waters to cancel, electrons cancel, and this is all we would have left. Hydrogens would cancel too, right? So the final thing down here would be 2 here, 1 there, 2 there, and 1 there. And no hydrogens and no waters evident in the equation. But we're told it's in acidic solution. We have to be told that, otherwise you can't tell it from the equation. Right? If you're just given that equation, you can't tell if it's acidic or basic. Right? That's one of those odd cases. All right. Whatever they're using on this board, I like that. That was 2. Let's see, how about 3? The following reaction occurs in aqueous acid solution. In the balanced equation, the coefficient of water is. Okay, we've got a nitrate ion. Is that an iodide? Yep. And it goes to iodate ion and nitrogen dioxide. Okay. So that's the oxidation state of iodine. On this side, we have -6 there for this oxygen, but we got to hold 1 out. So this is a +5. How about this one? -2 times 3 is -6. Hold 1 out for that minus. This one's a +5. -2 times 2 is -4. Neutral compound, +4. Okay, so far so good. Now we need oxidation reduction reactions. Okay, let's see. Nitrogen goes from a +5 to a +4. Oxidation or reduction? Yeah. Right, we had to add 1 negative to this one to get to that point. So it goes down here. NO3 minus. And it yields NO2 there. I'm going to go ahead and add an electron in there. Just needs 1 electron to get to there. And then we'll go here. This must be oxidation. Here to here. Let's see. We had go from -5 to -1 to +5. How many electrons do you have to lose? The way I do it is I go from minus to 0. You got to lose 1 there, right? And from 0 to +5, you got to lose 5 more. So that's 6. Let's see, nitrogen, 1 nitrogen, 1 iodide on both sides. That's good. Now we'll balance the oxygens. We need 3 of them on this side, right? And that means we need 6 hydrogens on this side. Okay. 3 oxygens here, 2 here. We need 1 more here. And then balance the hydrogens. Now we balance the electrons. We got 6 electrons here, only 1 here. We need 6. 6. Like green. 6. 12. 6 and 6. Now we can put it together. Except, can we answer the question without going to that trouble? What's the coefficient of water? Well, we've got 3 waters on this side and 6 on that side, correct? So that means we're only going to have 3 down here. This one goes out, that one becomes a 3. So our coefficient for water is 3. Right? You save yourself some time, not have to go all the way through. All right. That was 3, 4 coming up. All right. The following reaction occurs in basic solution. All right. That's chlorine plus water yields O2 plus F minus. Okay, so this one is an oxidation state of 0, and that was a -1. This one's a 0. This is a -2, and this is a +1. Okay. So which is the oxidation step? Oxygen went from -2 to 0. It'll lose 2 electrons, didn't it? So we go from water to oxygen. And let's see, just so I don't forget what I just said, we lost 2 electrons. Okay. Reduction step. That means F2 went to F minus, and it lost how many? From 0 to -1. Oh, excuse me, reduction. It gained 1 electron per fluorine. Right, but we got 2 fluorines. So we need 2 here and 2 there. And this oxygen, we need, it was 2 electrons per oxygen, wasn't it? So we need 2 here to give us 2 oxygens. Hold on a second. Yeah, we already got water, right? So we don't have to add water to this one. Water's already there. So 2 oxygens, but now we need 4 electrons. Total. Now need to reconcile the hydrogens. There we go. Just checking my numbers. Okay. So now we need to balance the electrons. We need 4 down here. So that's 2 here. 4 there. And 4 there. Now we are going to have to put these together because we got to do the hydroxyl trick. Well, let's bring them down. Well, let's see. We can cancel the electrons. And that's it. So let's put them in the same order. 2 F2s plus 2 H2O on this side. And on this side, we have oxygen first here, plus 4 F minus, plus 4 hydrogens. So now how do we convert it to basic? Add hydroxyls. We need 4 hydroxyls here. Why? Because 1 hydroxyl and 1 hydrogen equals 1 water. So we put these together, and that makes 4 waters. But we need hydroxyl on this side also. 4 hydroxyls. Okay. Nope, we're not done yet. Okay, you following me? Okay. 2 waters here. Now there are only 2 waters there. Okay, what was the question? Sum of the coefficients. Okay. This one's out. 2 plus 4 is 6, plus 1 is 7, plus 4 is 11, plus 2 is 13. That would be D. 13 is the total on the coefficients. Right, that was 4. Let's skip down to 7. Yeah, get them all in there. Number 7. For the redox reaction, 2Fe2, 2 plus Cl2 yields 2Fe3 plus 2 Cl minus, which of the following are the correct half reactions? Okay. We did a half reaction thing before, but I suspect there's going to be a twist to this one. Plus 2 Cl minus. Okay. All right, we got our oxidation states already. We go from 2 plus to 3 plus would be what? It's a loss. 1 electron per iron times 2 equals 2 electrons. I'm just checking the totals. For this one, we went, and it appears that this is balanced, right? 2 iron, 2 iron, 2 chlorine, 2 chlorine. And all we have to do is check the electrons to be sure they're balanced, and then we're good. As far as balanced equation goes. It doesn't say balanced up there, so we better check it. This goes from 0 to -1, which is a gain. Right? Gain 1 electron per chlorine, but we got 2 chlorines. Equals 2 electrons. Okay, so it is balanced. All right, so what would the half reaction for, let's see. They did the chlorines are the first ones in that list, so we'll do that one first. So the half reaction here is just this one. The gain, gain 2 electrons yields 2 Cl minus. This is the reduction. So the oxidation would have iron in it. Yields 2 Fe3 plus 2 electrons. Correct? We can simplify this one though. Right? 2, 2, and 2. Divide by 2. So it's only Fe2 plus, Fe3 plus, and 1 electron. So let's see. This one would be Roman numeral 1. And this one would be 4. Correct? So that's A is the correct answer there. That was the trick. Simplifying this one. Because if you were going to go look this one up in the standard reduction table, you wouldn't look for 2, 2, and 2. You'd look for this one, that one, and 1 electron. Okay. I think that's what they're getting at here. Because we could separate these into 2 half cells and make a galvanic cell out of it. Of course, it wouldn't be that easy because you got to have chlorine gas at 1 atmosphere pressure, and then you have a platinum electrode inside that delivery mechanism for the gas to collect the electrons. We're not going to have you do that. We don't have the equipment for it. Okay, number 8. How many electrons are transferred in the following reaction? Okay, 2 ClO3. Let's write it down here. 2ClO3 minus and 12H plus. I'm thinking this one is already balanced. And 10 iodide yields what? 5 iodines. That's easy to read from here. Cl2 and 6 water. Okay, that's a 0, that's a 0, that's a minus, that's a plus. Minus 2 times 3 is minus 6, hold 1 out. This is a plus 5. Okay. So let's do it this way. Let's just draw our connector lines. If this chlorine is going from plus 5 to 0, it had to lose 5 electrons. Not gain 5 electrons. You're not going to let me get away with that? Probably. Had to gain 5 electrons. So that's the reduction step. 5 electrons per chlorine, but there are 2 of them, right? So that's 10 electrons. Now, if the oxidation step gives us 10 electrons, then we got our answer, right? Hydrogen doesn't change. Oxygen didn't change. Iodide changed. Right? It was a loss of 1 electron per iodine. And how many iodines do we have? 10 electrons. So 10 electrons were transferred. Alrighty. Eight. Moving on to 11. Consider a galvanic cell based on the reaction Fe2 plus dichromate 07 yields Fe3 plus Cr plus in acidic solution. Calculate the voltage of the standard cell carrying out this reaction. All right, we're just looking for this value right here. So what we need to do is decide which one's oxidation and which one's reduction. So this iron went from 2 plus to 3 plus. It had to lose 1 electron per iron. That means this chromium had to gain. And since we're only looking for standard potential, we really don't have to calculate which one's which. We've already decided this one is the reduction, and this is the oxidation. So really all we need to do is look up the standard potentials, right? And I didn't even do that. Standard potential for Fe, that's a loss. So it's going to be 3 plus the standard reduction potential. Should be this way, right? We wrote it as an oxidation, but we're looking for the value for that equation. And then the other one is going to be a gain. So it's going to be Cr2O7 2 minus, and it's going to Cr3 plus, but it's in acidic solution, so that may make a difference in the value we look up. So we need to go down to the standard potential table. Come on, it's thinking. There we go, we're getting close. Oop, not close enough. There we go. Okay, we need, which one's got chromium in it? Chromium. I'm searching. Chromium. It's not on that side. Is it on this side? I missed it. There it is right there. Right here. Okay. So that's got dichromate on this side. Yeah. Dichromate to chromium 3 plus. And what's the standard potential for that one? 1.33. Standard potential for iron is almost straight across. Nope, that's the wrong iron. Here it is. Right. Nope, that's not it either. Where's the iron? So on this side, there it is right there. Okay. So 3 plus to 2 plus as written, yes. And that one is 0.77. Okay, these are both written as reductions. Let's see. How many electrons it said. I better be consistent here. 6 electrons. Right, when you're doing standard potentials, that doesn't matter. It just matters these values here. Because this is intensive property. All right, so if this one is going to be the oxidation, that means this one becomes negative. And then when you put them together, you get 7 and 13 is 6, 7 and 12 is 5, 0.56 volts. Okay. We just have to flip this one around. Like that. Make sure it's, this is the anode. This is the cathode. Okay. Now, 11. I need to go back up to 11. Let's see if I can do it this way. It's going to take forever. Let me do it this way. There we go. And scoot you back over. There we go. So the answer is D. 0.56 is the standard potential. Now, if we wanted to determine the actual value for the potential for this cell, we'd have to know the concentrations. And we'd have to put these together in with the waters and the hydrogens included in order to calculate the Q. Right? So we couldn't do this, the actual potential for this cell with the information we're given. Just a side note, in case you were wondering. All right, let's look for the next one. Let's see. Which of the following statements is false? All right, so we're going to have to either change the zoom or scroll a little bit. I think I'd rather scroll. A strip of copper is placed in a 1 molar solution of copper nitrate. Okay, 14. We have a solution of copper nitrate. It's 2 aqueous. And we have a strip of copper here. All right, so far so good. Oh, 1 molar concentration. Let's see. And a strip of silver is placed in a 1 molar solution of silver nitrate. I don't know which side to put it on yet, so I'll put it over here. So this is silver nitrate. Yes, 1 molar. and silver there. Okay. Two strips are connected to a voltmeter by wires, and the salt bridge connects the solutions. Okay, so we've got a salt bridge here. And then this is connected to a voltmeter. There we go. So far, what's the question? Standard potentials. All right, so the standard reduction potential for this one is 0.80. And the standard reduction potential for this one is 0.34 volts. Okay, which of the following statements is false? We may not have needed all that stuff, but I put it up there anyway. Electrons flow in the external circuit from the copper electrode to the silver electrode. Okay, so we do need to determine which one's which. Which one's the cathode, which one's the anode. I look at the voltages. If we're talking about standard conditions, which is right, 1 molar, 1 molar, then which one can we make negative and still come out with a positive value? Has to be this one, right? So it actually needs to be the other way around. This needs to be the anode at 0.34. So electrons are going to flow this direction. Is that true? Electrons flow copper electrode to silver electrode. Yes. A is true. How about B? The silver electrode increases in mass as the cell operates. Yes, it does. These silver ions are going to add an electron and be plated out on that electrode, so it will increase in mass. Okay. There's a net general movement of silver ions through the salt bridge to the copper half cell. No. Can't be. Silver ions are not moving that direction. They're moving on here. They're being plated out here. They're not moving that way. Right? So this one's false. Oh, we found our answer. Because we don't have any squirrely ones like 2 of the above or none of the above, that thing. So if you're taking a test, that's stop. We found our answer. That means D and E should be true. 15. Now you may not have to draw a picture to get the idea, but I like pictures. Which of the following species cannot function as an oxidizing agent? All right, let's put them up here. A, B, C, D, and E. So we got sulfur solid, NO3 minus, aqueous, Cr2O7 minus, aqueous, iodine, yes, and NO4 minus. All right, which one cannot function as an oxidizing agent? So what do we mean by oxidizing agent? What happens to an oxidizing agent? Oxidizing agents are reduced. So which one of these cannot be reduced? Could we reduce sulfur? We go from 0. You know, this is a good place to look at your periodic table at the back of your, because in the periodic table, you have oxidation states given in the upper right-hand corner of each of those little squares. And they tell you whether you can go more negative or more positive than your existing value. So sulfur is 0. Can sulfur go, can it be reduced? Yeah, it can go to -2, right? So it could serve as an oxidizing agent. How about NO3? Well, oxygen is not going to do anything. probably. We have to pick one, and we're going to pick nitrogen. So this is -6, so this is +5. So can nitrogen +5 be reduced? Let's see. Oh yeah. It can go all the way up to -3. All right, so that's a good one. We already did this one. This is +6, and in a previous example, it went to chromium 3+. Right? It can be reduced. How about iodine? Iodine -1. No, that's the most reduced it can get. There's the one. That's not going to serve as an oxidizing agent. Okay, and it makes sense, right? Iodine with one negative charge is what? It's got a complete octet. It's perfectly happy the way it is. Right? Try to force more negatives on that one, wouldn't you? Where are they going to go? Well, they got to go to the next highest valence level, right? That's very difficult to do. I'm sure some graduate student somewhere has been forced to do that project and done it. But for our purposes, it would not serve well as an oxidizing agent. And MnO4, we can do that one and look at it, and it would also work. Right? So this is the one that doesn't want to be reduced. Let's say scroll just a tiny bit and get 16 in here. How are we doing on time? You know what? Would it hurt anybody's feelings if we didn't do the lab today? Because we really do need to get through this review. And I'm afraid I'm going to run into lab time. So let's just see what happens. If you really want to do the lab, oh, I don't have a demo on this one. Right. So if we don't do it today, it's gone. It just won't be part of the mix. Okay. And with the end of the semester crunch, that's probably not going to hurt anybody's feelings. Everybody got a full load? Or more than a full load? Okay. So let's see what happens. Which metal, aluminum or nickel, could reduce zinc 2+ to zinc if placed in a zinc 2+ aqueous solution? Okay. So if we're going to reduce Zn 2+ to Zn 0, we need 2 electrons, right? And it's written as written, its reduction potential is -0.76. And we want to reduce it. So it has to stay that way. And the other options we have are aluminum 3+, and 3 electrons yields aluminum. But this is reduction. Right? So we're going to do it that way first. -1.66. And then nickel. We'll get 2 electrons and yield nickel solid, 0. And this one would be -0.23. Okay, if this is going to be reduced, these have to be flipped. They have to be oxidized in order to reduce this one. They have to be reducing agents. That means they have to be oxidized. So if we flip it back the other direction, and it changes signs, and then add the two together and see what you get. Well, a -0.76 and a +0.23 is not going to work. It's not spontaneous. Right? It gives you a negative value. But with aluminum, that does give you a positive value. Right? So the E for the system, E0 for the system, these two would be a positive value. These two here would be a negative value. So the aluminum is the only one that'll work. Okay. Did I go too fast? Okay. All right. We're 17. Okay, this is a biggie. We're going to have to scroll a lot here. So consider the galvanic cells shown below. Contents of each half cell are written beneath each compartment. Standard reduction potentials are given. Okay. What is the E0 for this cell? Okay. In this case, all we need is the standard reduction potentials. What number am I? 17. I think I got two more following this that are based on the same reaction, so I better build it out. Which one's going to be the oxidation and which one's going to be the reduction? They may not be written in the correct order. Right? It could be bromine could be on the right and chromium on the left. So let's look at those values. Cr 3 plus electrons. 3 electrons, yeah, to make chromium solid. Okay, and the standard reduction potential here is minus 727. Okay, and then the bromine plus 2 electrons yields 2 Br minus, and its standard potential is plus 1.090 volts. Okay. So which one has to be flipped? You don't want to flip this one, you're going to get negative. So we got to turn this one into the anode. This one would be the anode. This one would be the cathode. And if we reverse the direction, that makes this one positive. Then we can add those together and we get a 7, 11, 8, 1.817 volts. A would be the answer there. Okay, so we know that chromium needs to go on the left and not on the right. See, the way it's shown there, it's on the wrong side by convention. Okay. So that was 17. Yeah, here it comes. 18. Is it made? No, it's a different one. It's different. Okay, let me scroll down a little bit more and see if that chromium and bromine crop up again. Do they? You don't see them again? Okay. So we can, I think this one is going to show up. Let me spell that, didn't it? This one's going to show up in 18 and after. So we probably ought to treat this one as a full-blown half reaction problem. All right, so the two half reactions, and we'll come back to the actual values in a minute. As soon as we get, what's the value of the E for this cell? We can do that one without even writing it on the board. Right, which one of those must be flipped in order to make the total positive? Right. If we flip the top one, you got a negative value total. If we flip the bottom one, then you have a positive overall. So the positive would be 1.506 minus 1.330. 6, 7, 1. 0.176. Oops. Yeah, that's right. Positive 1.76 C. Okay. So that gets 18. Now 19 is going to ask us what? When current is allowed to flow, which species is reduced? Oh, okay. Well, we determined that this one was the manganese step, right? And this one was the chromium step. So which species is going to be reduced? It's the one that stays the same as it was on top. MnO4, the manganese in MnO4 minus will be reduced. Okay. MnO4 minus. Oops. Did I lose anybody? Okay. All right. Here it comes. What's the value of Q for the reaction quotient? All right. Now we got to do some. Was that 19? I did 19. I didn't mark it up there, did I? Okay. 19. The answer is MnO4 minus was the species being reduced. In fact, the manganese in that polyatomic ion is the part being reduced. Now we do 20. All right, let's see if we can. We know that the manganese is going to be the reduction side, and the chromium is going to be the. We might be able to shorten this process a little bit. The reduction step we know is going to be the manganese side. So let's put MnO4 minus plus 8 hydrogens plus 5 electrons yields Mn2 plus 4 waters. Okay. And then the oxidation step is going to be the chromium only flipped. So it's going to be 2 Cr3 plus, plus 7 water. And then it's going to yield 1 Cr2O7, 2 minus, 14 hydrogens, 6 electrons. There we go. So that would be the oxidation step. Okay. Now we need to do is reconcile some things. First of all, let's see. 1 manganese, 4 oxygens, 8 hydrogens, 8 hydrogens. Is that right? 5 electrons? Should be. -2, -8, -7, 7. So plus 7, yeah, that's right. And this one, let's see. -2, -14, -12. 2 of these is plus 12, so it means plus 6. And this one's going, we need to lose 3 electrons for each one, and there are 2 of them. Okay, that's good. I'm satisfied. Now we can go to reconciling all the other differences. Electrons. We got 5 here, we need 6 here. But we got 6 there. So what do? How do you reconcile an odd and even? Multiply 6 times this one. So that one's 6. This one's 48. This one is 30. This one is 6. And this one is 24. Okay. And 5 times this one. So that makes this one 10. 35. 5. And what's 5 times 14? 70. Did I do that right? 5 times 4 is 20. Carry your 2 plus 5 is 7. Okay. And this one's 30. Okay. So in case we need it in the future, N equals 30 moles of electrons. Okay? I don't know if we're going to need it, but it's there. Now we need to reconcile some things. Okay. The electrons are going to cancel out, of course. Waters, we got 35 waters here and 24 there. So those 24 go out. And this one becomes 11, right? 11 plus 24 is 35. Hydrogens. We got 48 here and 70 there. That means all of these are gone. And 48 from that one is what? 22? Yeah. Okay, now we can add it together. All right. So we got 6 MnO4 minus plus 10 Cr. That should be big C, little r. Okay, plus. And then that was gone, that was gone. We're left with 11. Water. Okay. 1, 2, 3. Good there. Then we'll put manganese first here. 2 plus. And then 5 dichromates. Okay, that's 1, 2. Those are gone. Those are gone. Plus 22 hydrogens. There we go. Okay, we can't simplify it any farther. No. Okay. So now we need, what are the values? The concentration values. So that's where we go up here. And MnO4 minus is 0.1. 1 molar. How about chromium? 0.4. Molar. Water doesn't count, right? Not for a K or a Q calculation because it's a pure liquid. So what's next? Mn2 plus. Mn2 plus is 0.20. 0.20. And dichromate is 0.30. Molar. And hydrogen ions. Oh, we got lucky there. Both sides are 0.01 molar. Right? I don't know what to do if they're different because we've only got one term there. All I can think of is if we've got two different concentrations on one in one cell and one in the other, that you'd have to go back and not cancel out your hydrogens. Keep all those over here on this side, keep all these on that side, and put the values in for those. That makes sense? Then you could build your equilibrium expression with 2 hydrogen concentrations. That's the way I'd try it first. See if it worked. Okay, so what's our expression going to be? Well, if we're going to do Q, we need essentially an equilibrium expression. So we need, let's keep it simple. Instead of writing this in, these terms go in the numerator, correct? So manganese would be 0.20 to what power? 6. Times the next one, 30 to the 5th power. And then hydrogen ions, 0.01 molar to the 22nd power. Okay. So far, so good. Those are the products. Now the reactants go in the denominator. So this concentration, 0.10 to the 6th power. This one, 0.40 to the 10th power. And water doesn't count. So the rest is number crunching. Let's see if I can do it without making a mistake. Let's see. 0.2 to the 6th power. 0.2 and then 6. Get my power button. Okay. There's a value in there, and I'm going to multiply it by the next 0.3 to the 5th power. Times those, and 0.01 to the 22nd power. Okay. So in case I mess up in midstream, I'm going to write this term right here is 2.6092 times 10 to the minus 44. Okay. And then 0.1 to the 6th power. And then 0.4 to the 10th power. Multiply those together. And I get 40. How many zeros is on it? Okay, divide that one into the other one. Did I do that right? Hold on a second. Let me try that again. 0.1 to the 6th power. Okay. 0.4 10th power. Times. I did it wrong. One 1.0486 times 10 to the minus 10. Okay. So let me see. What's one like? Oh, I'm going to punch the numbers in again. Okay. Good thing I wrote them down. 6.02 exponent 44. So I can divide. I get 2.49 times 10 to the minus 34. Is it Q? No, I did something wrong, didn't I? What's it supposed to be? B. Okay, let's try that again. This time I'll go straight through with no intermediates. I know I did that one right. Let's do 0.1 into 6 divided. Okay. 0.4 to the 10th power. 2.37 minus 24. No, I must have done something wrong. Okay, let's try it again. First of all, did we put them in the right order? 0.2 to the 6th power. 0.3 to the 5th power. 0.01 to the 22nd. Unless that's not right. Is that right? Oh, you don't have the well, maybe you don't. 20. Before I go to all this trouble. Let's see. 6.522. Yep. And 6.10. Yep. Okay, that's right. So let's try it again. All right. 0.2 to the 6th power. 0.3 to the 5th power. Times 0.01 to the 22nd power. No, that's right. Okay, 0.1 to the 6th power. Divide that into it. 0.4 to the 10th power. Divide that into it. 1.5 times 10 to the minus 41. Yeah, there we go. That's the Q. Okay. Now I'm going to leave that there for a second. Let's see what's next. We might need it. What is the stoichiometric coefficient of H plus? All right, H plus. So 21, we did the Q. That's the Q. 21 looks for the coefficient of H plus. 22, right? 22.
Yeah, 22. And then this one, what is it asking on the same problem? What's the cell potential at 25 degrees? All right, I knew that was coming. So we need the Nernst equation, don't we? Everybody remember the Nernst equation? The actual E is equal to the standard E. Is it plus or minus? It's minus 0.0591. Divided by the number of moles of electrons times the log of Q, correct? Let's see, where am I? Yeah. Okay. So we need the E. We did that one before, didn't we? Well, we can do it again. 1.506, 1.506 minus 1.330. It's 0.176. (0.176) minus 0.0591 divided by 30 times the log of 1.5 times 10 to the minus 44. Okay, let's see if I can do this one without messing up. Let's see, I'm going to take the log first. 1.5 exponent -41. Take the log of that, then times 0.0591 times that divided by 30. Okay, and then it's a negative value with a negative in front of it, so it's a positive. Change that sign and add it to 0.176. Okay, 0.256 volts. Rounded off 0.26, right? Yeah. Okay. Now, if that type of question showed up on a test, you have to go through all of this just to get down to that one value. I don't think I'd do that one to you, unless it was an extra credit. I'll probably do something like give you the Q value and ask you what this is. Then that would be a simple calculation. Or ask you what's the coefficient of hydrogen in a balanced equation, and then you could go down to this point. Something like that. Let's see, that was 22, wasn't it? I keep forgetting to write the number up there. This is the answer to 22. There we go. This is the answer to 21. No, 20, right? This is the answer to 21. Right here. I hope I don't need this anymore. I don't think I will. See if we can give our brains a rest. Skip on down, skip on down. There we go. 30. Let me write the number first. There we go. The following has a potential of 0.92 volts. All right, so we got 2 Hg 2 plus aqueous plus hydrogen And then 2H plus is aqueous plus Hg to 2 plus. Okay. What's the question? If the concentrations of ions were 1 molar in the presence of hydrogen were 1 atmosphere. So this is 1 atmosphere. This is 1 molar. This is 1 molar, and this is 1 molar. Yeah, that's what they said. The E0 for the half reaction. Oh, the actual value measured in this electrolytic cell is 0.92, not galvanic cell, pardon me, is 0.92 volts. Okay. So what would be the E0 for the half reaction? All right, 2 plus goes to Hg2, 2 plus. So this one is what? This one is plus 1, isn't it? Because there are 2 of them. And this one is 2 plus, because there's only 1. So it is reduced. It goes from 2 plus to 1 plus. That's true. So as written, 2Hg plus 2 electrons is Hg2 to the 2 plus power, to the charge. So that's the reduction side. This is the reduction. This is the oxidation. It goes from 0 to plus 1. So this is oxidation, this is reduction. Oh. You know what it is, don't you? What's the standard potential? Standard reduction potential for that half reaction. It's written as a reduction, and it's against the standard hydrogen electrode. So that's the value right there, 0.92 by definition. Okay. Making it harder than it was supposed to be. Tricky. Get your brain geared up for a complex problem and then throw a simple one at you. It's give you a whiplash. All right, let's see what's next. Oh, we're skipping a lot of them. There must be a lot of repetition. Same types of problems. Okay. 44. An excess of finely divided iron is stirred up with a solution that contains copper 2 plus ion, and the system is allowed to come to equilibrium. And so we've got copper 2 plus aqueous, and we're putting iron in it, solid, and it's allowed to come to equilibrium. So what could possibly be the reaction? Well, we could go from copper to copper solid, and then iron would be something, 2 plus or 3 plus. I'm not sure which. Let's say for convenience, 2 plus. That's probably what you would expect. Transfer electrons from copper to iron. Copper is a more active metal than iron, so that's probably what will happen. Okay, if we do that and let it come to equilibrium, and then you put and filter out any of the solids. Oh, it does tell you solid copper and solid iron are still in solution. And then you insert into the remaining solution solid copper and solid iron electrodes. What potential develops between the 2 electrodes? The key word here is equilibrium. If that reaction goes to equilibrium, there is no electromotive force
involved, right? If you let it go to equilibrium and use the same solution that's left over, right? You can't get electrons to move between the two electrodes anymore. Okay, so that's another trick question. Answer is 0 volts. And that goes back to the derivation of the Nernst equation, where we said if it's at equilibrium, then this value here is equal to 0, which is equal to that times logarithm K. Because K stands for equilibrium. That means E equals this part right here, because the total has to be 0. All right. 49. You make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode in a zinc nitrate solution. If you could increase the concentration of aluminum, which of the following is true about the cell potential? Okay, first of all, we have to decide which goes which direction. Right. We have aluminum. Let's see, aluminum plus 3 electrons yields aluminum metal. And the other one is zinc. Zinc 2 plus 2 electrons yields zinc metal. Then we need to know we need to know the standard potentials for each one. Right. Instead of flipping through that one, let me just turn to the page here and find them. Aluminum. Here it is. Minus 1.66 volts. And zinc 2 plus is, just got to find it. Here it is. Minus 0.76. Okay, we have to assume that these are standard potentials. Otherwise, we don't know what our starting point is. So which one's the anode and which one's cathode? This one would have to be the anode, right? If you flip that one, you're still negative. Flip this one. So we're going back this way. Right? That makes this one the anode. This one the cathode. All right, so let's write this anode in the way it would be positioned with respect to the cathode. Then we can make some predictions, right? And this is going to be plus 1.66 volts. Okay. Now we can approach this problem from Le Chatelier's point of view. What would happen if we increase the concentration of aluminum? Right? Increase the concentration. Well, Le Chatelier says it's going to move back this way. Well, that's counter to the way we want it to move, right? It's going to move, the equilibrium is going to move toward reduction, and that runs counter to this reduction. So the voltage is going to drop. We're going to decrease the voltage. Okay? Now I should put this. Right. We'll decrease, actually, concentration doesn't matter. We're going to actually decrease the real voltage. Okay? I assume it's okay. I don't hear any objections.
All right, that was 49. $56. We might be able to do the latter today. How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours?
And so the current, which we designate as an I, this is from physics, is 14.4 amps, which is equal to 14.4 coulombs per second. That's what that means. Okay. And the time is 3.2 hours. Yeah, 3.20 hours. So we're looking for moles of electrons. Moles of electrons. Well, if you've got this much time for that current to go, I would start with the time. But we're not going to be able to cancel seconds with hours, right? We got to convert this to seconds. So how many seconds in an hour? Remember? 60 times 60. 60 seconds in a minute and 60 minutes in an hour. 3,600. That gets rid of the hours. Now we got seconds. Now we can say for that much time, we're running at 14.4 coulombs per second. Cancels the seconds, leaves us with coulomb. Now we need to convert coulombs to moles of electrons. And one, let's see, 96,000. Let's see. I'll find it. It's in here. 96,485. Coulombs per mole of electrons. So that should give us our answer. 3.2 times 3,600 times 14.4 divided by 96,485 is 1.72 moles of electrons. Okay. Little dimensional analysis there. $56, then keep it going. 64. What mass of chromium could be deposited by electrolysis of an aqueous solution of chromium 3 sulfate for 145 minutes using a constant current of 11 amps? Mass of chromium we're looking for. All right, so sulfate is a spectator. What you've got here is chromium 2 sulfate in solution actually yields 3 plus sulfate 2 minus. Right. Yeah, that's right. 2 comes over here, 3 goes over there. That's what gives us this one. So we're only interested in this Cr 3 plus. And we're going to reduce it to chromium metal. That's the equation we're worried about. That's the net equation. Okay. Except we need 3 of them, right? 3 electrons. We'll reduce that chromium 3 plus. Okay, now we'll need that later. But first we need how many electrons are being pushed through that solution. For 145 minutes, let's say time, 145 minutes at a current of what? 11 amps.
That's a lot. 11 amps. I don't know, what do they say? How many amps does it take to kill somebody? Stop their heart? Not much. Just a little bit. 11 amps would probably knock you on the ground. Let's see, 145 minutes, 11 amps. Oh, okay, so that's all we need to know. And we're looking for mass of chromium. Mass of chromium deposited. Okay, so if we're at 145 minutes, we need to convert that to seconds, right? Because amps is coulombs per second. So, excuse me. Go on top. 60 seconds, 1 minute. And so minutes cancel, we got seconds. Now we can take 11 amps, which is 11 coulombs per second. That cancels seconds. Now we need coulombs per mole of electrons. If I remember correctly, 96,345. Check myself again. 85, 485. 485. There we go. So that gives us the moles of electrons. Now, what's the ratio of moles of electrons to moles of chromium? Right? 3 electrons, 1 chromium, right? And then if we know moles of chromium, we can get mass of chromium. All we need is the molar mass of chromium, which is 5200. There we go. We can do it all in one calculation. Dimensional analysis. 145 times 60 times 11 divided by 96,000, oops, 485 divided by 3 times 52. And I get 17.2 grams of chromium metal are plated onto that object, whatever it is. Let's say it's a bumper. Okay. I don't know, maybe the most difficult part is where do you start? When we got an electrolysis going, I start with time and work it from there. All right, 64. Ah, 72. Did we do this one before? Dichromate iodine. I'm sure we did. Did we do that one previously? It was up toward the top. Chlorate and iodine. Oh, maybe that's the one I'm thinking of. Okay, I guess we didn't do it. And let's head to the bottom. What was I? There we go, 72. Okay. We're given this unbalanced equation in an acidic solution, dichromate plus iodine. Yield. Chromium 3 plus iodate. Okay. So we need to do That's -1 oxidation state, 3+ oxidation state. Let's see, -2, -14 total. Hold 2 out. Or +12, 2 of them means this is a +6. Okay. And this iodine, -2, -6, hold 1 out, -5, +5. Okay. Now we're going from chromium +6 to 3+. That's gain of 3 electrons, right? So that's the reduction step. Dichromate minus Br3+, and we need 3 electrons per chromium. So we need 6 electrons, right? Okay, let's skip the step. Oxidation step. Iodide and iodate plus how many electrons? Well, let's see. 6 electrons, right? We lost 6 electrons per iodine, and there's only 1. So that's good. Is that correct? Yeah, that's right. Okay, so now our electrons are already balanced. We just need to balance oxygens. So we need 3 oxygens here as water, and then 6 hydrogens here. And here we need 7 oxygens on that side, and then 14 hydrogens. Okay. So since our electrons are already balanced, we can just add them together. Okay. Can we cancel before? Yeah, we can cancel that one, that one. We can cancel these 6 hydrogens. That makes 8 here. We got 3 waters here and 7 there. So that makes 4 here. So in the end, 207, 2 minus, and plus iodide, and then plus 8 hydrogens yields 2 chromium 3+ plus 1 iodate, and then plus 4 water. All right. Is that what I got there? Yep, that's it. That's the balanced acidic oxidation production reaction for those 2. I'll scroll to the next one when you guys are ready. Oh, now we have one. We have one for. Need some more time?
Yeah, just 1 more second.
Okay, that's fine. No problem. Okay. All right, 75. This might be the last one. You may have time for the last after all. So in basic solution, BiO3 3 times. Okay. And then SNO2 2 minus yields bismuth metal and SNO3 2 minus. Yes. Okay. This is a 0. This hydroxyl is 3 minuses together.
So that means this one has to be a 3 plus. This one is -2 times 2 is -4. Hold 2 out, -2, so this is a +2. And this one is -2 times 3 is -6. Hold 2 out. 4. This is a +4. Oxidation state. Okay. If we go from 3 plus to 0, we had to gain 3 electrons. That's the reduction step. Three. And that was 3 electrons per visit. So we only need 3 electrons there. Did I lose somebody? Or are they just pulling into the parking lot? No, they're still there. Okay. And the oxidation step is the 10 O2 to minus to SNO3 minus. How many electrons? All right, we went from a 2 plus to a 4 plus, means we lost 2 electrons per 10. And there's only one of them, so that's good. Right? Okay. All right. So got to balance the oxygens now. 2 here and 3 there. That means we need 1 over here. And that means we need 2 hydrogens over here. Okay. Now the temptation here is to say, we got 3 hydroxyls here. Why don't we just put 3 hydroxyls over there? It might work. But if we do it the fake acid method, we need 3 oxygens over there. Like that. Right? We already have 3 hydrogens over here. With 6 hydrogens there, we only need 3 more hydrogens here to balance the hydrogens. That's where you could stumble. You don't remember that there are 3 hydrogens already over here. So when you come back with your hydrogens, you only need 3. Now we need to balance the electrons. So 2 there and 3 there means we cross multiply. This one is a 3 multiplier, and this one is a 2 multiplier. Right? 2 over here, 3 over here. Okay, so that means we need 3 here, 3 there, 3 there. 3 times 2 is 6. 3 times 2 is 6. And we use that one up. 2 here. 2 times 3 is 6. 2 times 3 is 6. 2 here. 2 times 3 is 6. We use that one. Okay. Now, let's see. We got 3 waters here, 6 waters there. So these 3 waters will go away. And these will go back to 3. Electrons, right? They're gone. And hydrogens, 6 hydrogens there, and 6 hydrogens there. They go away. Okay. So let's bring everything down. Put them in the order they are up here. 2 BiOH 3 and SNO2 minus 3 SNO2 minus. Nothing else. Okay, from the other side, we have 2 bismuth, don't need that. Not now. And then plus 3SNO3 minus. And then 3 waters. All right, we don't have any hydrogens to balance here. So where are the hydroxyls? Right there, same place they always were. This is in basic solution, just as is. Because this is going to be soluble as bismuth 3+ ion and OH minuses in solution. Okay. So that's a basic solution right there. All right. Got the last one? Yeah, that's the last one.